From the dawn of human consciousness, we have gazed at the night sky, captivated by its boundless mystery. Questions echo across the vast cosmic canvas. Are we alone in this magnificent universe, or do other forms of life, perhaps even intelligence, populate the stars? This ancient inquiry fuels our audacious hunt for alien life. For millennia, these musings remained confined to philosophy and mythology. But in the modern era, propelled by scientific curiosity and technological prowess, the search has transformed into a rigorous scientific endeavor. Astronomers, biologists, and engineers now collaborate, systematically probing the cosmos for any whisper of extraterrestrial existence. The very notion of alien life challenges our anthropocentric view, expanding our understanding of what life can be. It pushes the boundaries of biology, astrophysics, and even our most profound philosophical beliefs. This quest is not merely about finding a new species, it's about redefining our place in the universe. Our journey begins with context, the sheer immense scale of the cosmos. Our Milky Way galaxy alone contains hundreds of billions of stars, and there are trillions of galaxies in the observable universe. This staggering number implies an almost inconceivable number of potential homes for life. Every star, much like our Sun, potentially hosts a retinue of planets. Driven by advanced observational techniques, astronomers have confirmed the existence of thousands of exoplanets beyond our solar system, with countless more awaiting detection. This discovery reshaped our understanding of planetary formation. The concept of the habitable zone became central to this search. This is the region around a star where conditions are just right for liquid water to exist on a planet's surface, a fundamental requirement for life as we know it. Not too hot, not too cold, but just right. However, liquid water is not the only prerequisite. A planet also needs a stable orbit, a protective atmosphere, and potentially a magnetic field to shield it from harmful stellar radiation. These factors combine to create a truly promising candidate for supporting life. With the advent of space telescopes like Kepler and soon the James Webb Space Telescope, our ability to characterize these distant worlds has greatly improved. We can now infer their sizes, masses, and even glimpse clues about their atmospheric compositions. But what exactly are we looking for? Life on Earth provides our only template, yet it also showcases an incredible diversity that challenges narrow definitions. From the bustling rainforests to the barren Antarctic deserts, life finds a way to thrive in extreme conditions. These extremophiles, organisms that flourish in environments previously thought uninhabitable, expand our imagination. They survive crushing pressures, scalding temperatures, intense radiation, and even thrive in environments devoid of sunlight, relying on chemical energy instead. Life's tenacity on Earth suggests that if conditions are even remotely suitable elsewhere, life might emerge. This concept underpins astrobiology, the interdisciplinary field dedicated to understanding the origin, evolution, distribution, and future of life in the universe. The origin of life on Earth, abiogenesis, remains one of science's greatest mysteries. Was it a unique event, or is it a natural consequence of complex chemistry under certain conditions? Laboratory experiments have shown that organic molecules, the building blocks, can form spontaneously. If life arises readily, given the right inputs, then the universe might be teeming with simple microbial forms. This thought gives us hope that the vastness of space isn't an empty void, but potentially a cosmic biological soup in various stages of development. Our search for alien life primarily adopts two complementary strategies: passive listening and active detection. Passive methods involve scanning the cosmos for signals or signs that might betray the presence of life or technology without broadcasting our own. The search for extraterrestrial intelligence, or SETI, embodies this passive approach. For decades, SETI scientists have meticulously scoured radio frequencies, hoping to intercept a deliberate message or incidental electromagnetic leakage from a distant civilization. The radio spectrum is considered ideal for interstellar communication because radio waves can travel vast distances through space unimpeded by cosmic dust or gas. Specific waterhole frequencies linked to hydrogen and hydroxyl are often prioritized for their fundamental nature. Over the years, SETI has employed increasingly sophisticated instruments, from the Arecibo Observatory to the Allen Telescope Array. These facilities process enormous amounts of data, searching for non-random patterns that could signify intelligence. Beyond radio, optical SETI looks for deliberate flashes of light, perhaps powerful laser beams directed towards Earth. These signals, though harder to detect due to their transient nature, could transmit information at much higher rates. The challenge with SETI is that we are looking for a needle in an astronomical haystack, without knowing if the needle even exists or what it might look like. Any detected signal would require rigorous verification to rule out natural phenomena. But what if life doesn't communicate with deliberate signals? What if we could detect its presence through technosignatures, indirect evidence of advanced technology? This could include atmospheric pollution, artificial structures, or unusual energy consumption. For example, detecting significant levels of chlorofluorocarbons, a chemical unheard of in natural processes, in the atmosphere of an exoplanet could strongly suggest industrial activity. Or massive orbital energy collectors, known as Dyson spheres. However, interpretation of technosignatures is complex. What looks unnatural to us might be perfectly natural given different planetary conditions. The risk of false positives is ever present, demanding caution and multiple lines of evidence. While passive listening is the primary approach, some advocate for active SETI or METI, messaging extraterrestrial intelligence. This involves deliberately broadcasting messages into space, hoping for a reply. Proponents argue that waiting for someone else to make contact could take millennia, if it happens at all. By actively broadcasting, we accelerate the process and demonstrate our technological capabilities and willingness to connect. Conversely, many express grave concerns about METI. Sending signals might reveal our location and existence to potentially hostile civilizations. The consequences of such an encounter are unknown and could be catastrophic. The Silent Earth hypothesis suggests that advanced civilizations might deliberately remain quiet to avoid drawing attention to themselves, aware of the risks. This makes our active broadcasting a contentious ethical dilemma. Moving beyond communication signals, the search also encompasses direct detection strategies, primarily looking for biosignatures, chemical or physical evidence of life itself, regardless of its intelligence or technological development. The next generation of telescopes, like the James Webb Space Telescope, excels at analyzing the atmospheres of distant exoplanets. By studying how starlight passes through these atmospheres, scientists can identify the presence of specific gases. Certain combinations of atmospheric gases, like oxygen alongside methane, would be highly suggestive of active biological processes. On Earth, oxygen is primarily a byproduct of photosynthesis, and methane is quickly consumed, preventing their coexistence without life. While promising, biosignatures are not foolproof. Geochemical processes can sometimes mimic biological ones. Therefore, finding a single biosignature isn't enough. Scientists seek multiple converging lines of evidence to confirm life. Future observatories might even be capable of directly imaging exoplanets, resolving surface features or larger-scale vegetation patterns. Imagine seeing vast forests or swirling oceans on an alien world. Of course, the most immediate and thrilling possibility for finding life lies within our own cosmic backyard, the solar system. Here, robotic probes can directly visit and sample environments, offering a far more detailed investigation. Mars, our celestial neighbor, has long captivated our imagination. Early observations of canals proved false, but evidence now confirms Mars once hosted liquid water on its surface for extended periods, making it a prime candidate for past or present microbial life. Rovers like Curiosity and Perseverance have explored ancient lake beds, analyzing soil and rock samples. They've found complex organic molecules, carbon-containing compounds essential for life, although not necessarily signs of life itself. The subsurface of Mars is of particular interest. Protected from harsh surface radiation, any remaining Martian life might persist in underground aquifers. Future missions plan to drill deeper, seeking these protected havens. Beyond Mars, several icy moons in the outer solar system present intriguing possibilities. Europa, a moon of Jupiter, is believed to harbor a vast subsurface ocean beneath its icy shell, warmed by tidal forces from its massive parent planet. This ocean could contain more water than all of Earth's oceans combined. Evidence from the Hubble Space Telescope suggests plumes of water vapor erupting from its surface, potentially offering a direct way to sample its interior without drilling. Similarly, Saturn's moon Enceladus also boasts a subsurface ocean, confirmed by the Cassini spacecraft, which flew directly through its geysers. These plumes contained water, salts, and complex organic molecules, all ingredients for life. The discovery of hydrothermal vents on Earth's deep ocean floor, supporting diverse ecosystems without sunlight, provides a powerful analog for these icy moons. Such vents could exist on their ocean floors, fueling alien life. Titan, Saturn's largest moon, is unique. It possesses a thick, nitrogen-rich atmosphere, lakes of liquid methane and ethane, and a complex organic chemistry. While too cold for liquid water on its surface, an underground water ocean might exist. Could life evolve in liquid methane using a different biochemistry than water-based life? Titan offers a fascinating test case for alternative forms of life, pushing the boundaries of our biochemical understanding. Even lesser-known candidates, like the dwarf planet Ceres with its briny cryovolcanoes, or Triton, Neptune's largest moon with its nitrogen geysers, present tantalizing, albeit distant, possibilities for finding some form of simple life. The search for life is not just about finding it, it's also about understanding the profound implications of its existence. This leads us to the great silence, eloquently articulated by the Fermi paradox: where is everybody? Given the vast number of stars, Earth-like planets, and the presumed ease of life's emergence, along with the immense timescales involved, statistically advanced civilizations should be common. Yet, we detect no signs of them. Many proposed solutions to the Fermi paradox exist. Perhaps intelligent life is incredibly rare, emerging only under a unique confluence of improbable events. Earth might be a fluke, a cosmic lottery winner. Another hypothesis is the Great Filter. This theoretical barrier suggests that there is some evolutionary stage that is extremely difficult, if not impossible, for life to overcome, preventing it from reaching interstellar communication capabilities. This filter could be in our past, the origin of life itself, the emergence of complex cells, or the development of intelligence. If so, we are incredibly fortunate to have passed it, implying life must be rare. Or the filter could be in our future: global catastrophes, self-destruction through technology, or environmental collapse. This is a sobering thought, suggesting that intelligent civilizations perhaps inevitably destroy themselves. Alternatively, perhaps civilizations reach a certain level of advancement and then choose not to communicate, or they transcend biological forms and become purely digital, existing in ways we cannot detect or comprehend. Deeper still, the zoo hypothesis proposes that advanced civilizations are aware of us, but choose not to interfere, treating Earth as a protected preserve or conducting a cosmic experiment, letting us develop naturally. Another solution suggests that the vast distances and timescales make communication impractical. Even at light speed, messages could take thousands of years to traverse galaxies, making a meaningful dialogue impossible. The implications of discovering alien life, whether microbial or intelligent, would be profound. It would fundamentally alter our scientific understanding across myriad fields. Biology would gain new templates, physics new challenges. Philosophically, the discovery would challenge our unique position, demanding a re-evaluation of anthropocentrism. Are we special, or just one among countless iterations of life? This question has deep spiritual and existential implications. Societally, a confirmed discovery would likely trigger a global response, uniting or dividing humanity. How would religions cope? Geopolitics, economics, these are complex questions that demand serious foresight. If the life is intelligent, ethical considerations become paramount. How do we communicate? What do we share? What are the protocols for interaction? These are not merely hypothetical debates. They are preparations for a potential future. The very act of searching fosters international collaboration, pushing the boundaries of technology and inspiring a new generation of scientists. It reminds us of our shared humanity and our shared smallness in the universe. Looking ahead, the future of the search is bright, driven by ever-improving technology. New techniques for exoplanet detection, like astrometry and microlensing, are constantly refining our catalogs of potential homes. Next-generation space telescopes, such as LUVOIR and HABEX, are being designed with unprecedented capabilities. They aim not just to detect, but to characterize exoplanet atmospheres in exquisite detail, searching for complex biosignatures. The concept of bioindustrial signatures is also emerging, a blend of biological and technological signs unique to a civilization that has profoundly reshaped its planet through engineering, like larger-scale terraforming projects. And within our solar system, upcoming missions are specifically designed to answer the life question. NASA's Europa Clipper and ESA's JUICE mission will conduct detailed flybys, preparing for potential landers or submersibles. Similarly, probes like Dragonfly are set to explore Titan, providing us with our first direct look at its fascinating chemistry. These missions represent humanity's tangible steps towards answering the age-old question. Breakthrough Listen is expanding SETI's scope, using the world's most powerful telescopes to scan millions of stars across a vast range of frequencies, dramatically increasing the chances of detecting a signal. The search is also becoming increasingly multidisciplinary, integrating fields like artificial intelligence and machine learning to sift through the immense datasets for subtle patterns that human eyes might miss. Citizen science initiatives, like SETI at Home, have allowed millions of volunteers worldwide to contribute their computing power to the search, democratizing scientific discovery and fostering a shared sense of cosmic adventure. The scientific community is also establishing protocols for contact, hypothetical plans for how humanity would react, and what steps would be taken if unambiguous evidence of extraterrestrial intelligence is found. These protocols emphasize verification, careful assessment of the signal, and a global, unified response, avoiding hasty declarations or unilateral actions. The stakes are simply too high for anything less. The hunt for alien life is a testament to humanity's insatiable curiosity and our relentless drive to explore the unknown. It's a journey not just to outer space, but into the very nature of existence. Whether we find microbial organisms clinging to life in subsurface oceans or receive a faint, coded message from a distant star, the discovery of alien life would be one of the most transformative events in human history. It would challenge our anthropocentric biases, forcing us to reconcile with the vastness of the cosmos and the myriad possibilities it holds, expanding our definition of life itself. In a universe of billions of galaxies, each with billions of stars, the idea that Earth is the only place where life took hold seems increasingly improbable. The odds simply favor life existing elsewhere. The pursuit of life beyond Earth is more than just science. It is a profound philosophical quest, a mirror reflecting our own identity and significance against the cosmic backdrop. The very act of searching cultivates a cosmic perspective, reminding us that we are all inhabitants of a pale blue dot, unified by the common experience of contemplating our place in the grand tapestry of existence. The whispers from the stars are faint, sometimes imperceptible, but they persist. And as our technology advances and our understanding deepens, our ears become more attuned to these cosmic echoes. The audacious hunt continues, a testament to humanity's enduring spirit of exploration and its profound desire to connect with the unknown. We are listening, we are searching, and the universe is vast. The concept of Goldilocks zones extends beyond planetary surfaces to deep subsurface oceans. If conditions for liquid water and essential chemicals exist underneath a moon's icy crust, life might not even need sunlight. This subsurface habitable zone dramatically expands the number of potential life-bearing worlds, encompassing bodies that might otherwise seem inhospitable, such as icy dwarf planets or even rogue planets wandering between stars. The potential for life in extreme conditions also requires us to consider alternative biochemistries. While carbon and water are fundamental on Earth, other elements and solvents could form the basis of life in different environments. For instance, silicon, which can form elaborate compounds, might substitute for carbon in extremely hot scenarios. Or ammonia, liquid at very low temperatures, could replace water as a solvent for life in frigid environments. This necessitates an open mind, challenging our Earth-centric assumptions. The universe's creativity might far exceed our wildest imaginations, producing life in forms utterly alien to our current understanding. The detection of phosphine in Venus's atmosphere, though widely contested and currently unexplained by known geological processes, briefly sparked excitement, suggesting that perhaps even seemingly hostile environments could harbor life. While likely a false alarm, the Venus phosphine incident underscored the importance of rigorous scientific validation and the immense challenge of distinguishing biological from abiotic processes across vast distances. Geological activity on exoplanets also plays a crucial role. Volcanism can release gases vital for sustaining atmospheres and circulate nutrients, creating dynamic environments conducive to life's emergence and evolution. Plate tectonics, unique to Earth in our solar system, is thought to be critical for long-term climate stability and the cycling of crucial elements. Could it be a prerequisite for complex life? The stability of a star is also paramount. Variable stars, prone to intense flares, might strip away planetary atmospheres or sterilize surfaces, making sustained life difficult or impossible. Our Sun, a relatively stable G-type star, has provided billions of years of consistent energy, allowing life on Earth to evolve from simple microbes to complex multicellular forms and ultimately intelligence. Red dwarf stars, far more numerous and longer-lived than Sun-like stars, represent a vast, unexplored frontier for life. Though prone to flares, their extreme longevity offers billions, even trillions, of years for life to potentially emerge. Planets orbiting red dwarfs might be tidally locked, presenting extreme temperature gradients. Yet, scientists theorize that thick atmospheres or ocean currents could distribute heat, creating habitable areas. The concept of panspermia, that life could travel through space, carried on meteoroids or comets, offers another potential pathway for life's distribution. If true, life might be more common than independent abiogenesis suggests. Microbes on Earth have shown incredible resilience, surviving exposure to the vacuum of space and extreme radiation for extended periods. This suggests that life could indeed hitchhike between planets or even star systems. This idea shifts the question from where did life begin to where did life arrive from. It means that once life gets started somewhere, it might then spread widely across a solar system or even beyond. The discovery of extremophiles on Earth also pushes us to redefine the very concept of life. Is it only carbon-based and water-dependent, or can it manifest in forms fundamentally different from our own? Some hypothesize that life could exist not on planets, but within vast nebulae, forming complex structures from cosmic dust and gas. This stretches our imagination beyond the familiar planetary paradigm. Or perhaps life could manifest as sentient plasma entities within stars, or as computational intelligence operating at the quantum level. These radical ideas, while speculative, highlight the boundless scope of the search. The concept of consciousness itself, its origins and potential universality, adds another layer of complexity. Is consciousness a unique terrestrial phenomenon or an emergent property common throughout the cosmos? The ongoing research into protolife, the transition from non-living chemistry to self-reproducing systems, provides crucial insights into the likelihood of abiogenesis occurring elsewhere. Complex organic molecules, including amino acids and sugars, have been found in meteorites and nebulae, suggesting that the building blocks of life are abundant throughout the universe. The future of astrobiology also involves a deeper understanding of planetary formation and evolution. What makes a planet truly Earth-like versus merely rocky? The nuances are increasingly important. The habitability of a planet isn't static. It evolves over billions of years. A world once suitable might become barren, or a seemingly dead world might awaken into life. Time itself is a key factor. The concept of a galactic habitable zone suggests that life might be more likely to emerge in certain regions of a galaxy, away from the chaotic galactic center and intense radiation zones. Too close to the center, and supermassive black holes and supernovae might sterilize planets. Too far out, and there might not be enough heavy elements to form rocky planets. Even the search for life in our solar system requires incredibly specialized instruments, capable of detecting trace biosignatures in challenging environments, distinguishing them from contaminants. Contamination is a major concern. Bringing Earth microbes to another planet could irrevocably alter its ecosystem. Conversely, bringing alien microbes back to Earth requires extreme planetary protection measures. The ethical implications of deliberately seeking contact, or METI, remain contentious. If we do make contact, who speaks for Earth, and what message should we convey? These critical questions lack universal consensus. Some argue that humanity should first address its own planetary and societal challenges before venturing into unknown cosmic encounters. The resources and focus could be better spent at home. Yet the allure of discovery is powerful. The prospect of understanding whether life is common or a true rarity fundamentally changes our perspective on the uniqueness and fragility of our own existence. The sheer joy and wonder inspired by the search for alien life transcends national borders and cultural differences. It unites us in a shared aspiration to unravel the universe's deepest secrets. The astronomical community is developing SETI protocols for what to do if a signal is detected, stressing verification and open communication before any public announcement. The search for technosignatures is growing beyond radio and optical signals. Scientists are exploring novel ideas, like looking for evidence of interstellar probes or relic megastructures. Perhaps the most crucial aspect of the hunt is the relentless pursuit of knowledge, driven by an inherent human desire to peer beyond the veil of the unknown, to understand our universal context. Every new exoplanet discovered, every new understanding of extremophiles, every technological leap forward brings us closer to an answer, whether it confirms our uniqueness or reveals us to be part of a larger cosmic community. The existence of life, in any form, anywhere else, would profoundly reshape biology, challenging our assumptions about evolution and adaptation, and opening entirely new branches of scientific inquiry. It would prompt us to ask whether there are universal laws governing the emergence of life, or if each instance is a unique cosmic experiment, a testament to the universe's infinite creative potential. The discovery of intelligent life, however, would be a watershed moment, unprecedented in human history. It would force a reconsideration of our moral frameworks and planetary priorities. It would pose fundamental questions about our shared evolutionary paths, potential conflicts or alliances, and the ultimate destiny of intelligent species in the universe. The universe does not provide easy answers. The search is a marathon, not a sprint, demanding patience, perseverance, and a willingness to embrace uncertainty. But the very act of searching, the audacious ambition to seek out life beyond our home planet, says something profound about who we are as a species: curious, hopeful, and endlessly seeking to understand. The future will undoubtedly bring new instruments, new methodologies, and perhaps the long-awaited evidence. Until then, we continue our cosmic vigil, ever vigilant for the whispers from the stars. The hunt for alien life is humanity's greatest scientific adventure. It is a journey into the unknown, driven by the profound question, are we alone? And the answer, whatever it may be, awaits us among the stars. From the primordial soup on distant worlds to the intricate techno-signatures of advanced civilizations, the possibilities are endless. Our understanding of life's potential is only just beginning. The journey has just begun. The universe, in its boundless majesty, continues to hold its secrets, but humanity, driven by a relentless spirit of discovery, continues to listen, to observe, and to dream. We expand our cosmic vocabulary, learning to read the subtle chemical fingerprints in atmospheres and the faint whispers across cosmic distances. Each datum is a potential letter in an alien alphabet. The search is global, attracting minds from every continent, transcending political boundaries in a shared pursuit of knowledge that affects all humankind. The universe constantly surprises us, revealing phenomena that challenge our preconceptions. This humility is key to the search. We must be prepared for anything. The very difficulty of finding life only underscores the value of Earth as a living world. It also highlights the incredible cosmic lottery that allowed us to exist. If life is common, it implies a certain universality to biological processes, suggesting deep, underlying cosmic principles at play. If life is rare, then our existence becomes even more precious, a profound responsibility to protect and nurture the unique biological experiment that is Earth. The questions posed by the hunt for alien life transcend science, touching on our deepest philosophical ponderings about purpose, meaning, and our ultimate place in the cosmos. Indeed, the act of searching changes us. It expands our horizons, inspires technological innovation, and forces us to confront our assumptions about life and intelligence. The universe is patient. It has observed billions of years of cosmic evolution. Our search, however long it takes, is but a fleeting moment in its vast history. Yet it is a moment defined by an unparalleled intellectual adventure. The whispers from the stars continue, challenging our isolation, inviting us to imagine a cosmic community. The quest for life beyond Earth is humanity's profound statement to the universe. We are here, we are listening, and we are ready for whatever truths you may reveal. The search promises not just scientific answers, but existential revelations. It is a testament to the enduring human spirit, forever looking upwards, forever seeking connection. And so, the audacious hunt for alien life continues, a journey not merely to find others, but in doing so, to truly understand ourselves. The stars await our discovery.